Hey everyone, so these are the solutions to Worksheet 3.1. Here we're going to be introducing the idea of polynomial functions and getting a better understanding of how they work and what their graphs are going to look like. So with number 1, we've got a function g of x defined as 3x to the power of 5 minus 2x squared plus x plus 1. So here it kind of breaks it down into different steps to kind of define some of the key characteristics of this function and bringing it to how we can predict what this curve may in fact look like. So the first thing that we're looking at is something called the degree of the polynomial. The degree of the polynomial is always going to be the greatest power of any of the exponents of x or whatever our independent variable may be. In this particular case, the greatest exponent here is 5. So this would represent the degree of the polynomial. So in this case, we would just say that the degree of this polynomial is 5, or we could call it a 5th degree polynomial. Now in part B, we want to find the leading term and the leading coefficient. These are going to be particularly important in terms of being able to predict characteristics like end behavior as we get into that. So the leading term, and it's often called the dominant term as well, it's always going to be the term that has that greatest power of x associated with it, where we were concerned with that and finding the degree. So for the leading term, what we're going to do is we're going to go up to the polynomial and find the term that has that greatest power of x, wherever it may be. So in this case, the leading term would actually be 3x to the power of 5. And then that leading coefficient is just going to be the coefficient associated with that lead term. So here the lead coefficient is going to be 3. Now we're particularly interested in whether or not the lead coefficient is positive or negative, as well as if the degree is even or odd, because there we can make some predictions about the behavior of the curve from there. Okay, so now we want to find the constant term, and that shouldn't be too bad. Here the constant term is really just ran out of colors here. So the constant term is going to be the term that is the constant. It may be there, it may not be present, but in this case we do have a constant term of plus 1, and we can go ahead and we can identify that. So our constant term in this case is just going to be 1. And the thing to keep in mind about this and why the constant term might be important is this is going to end up being, provided that we have our polynomial written out here in general form, that constant term is going to be our y-intercept. So this is the y-intercept. And again, we can get that because if we were to take this function g and evaluate it at 0, we would just get that 1 back. So we've picked up some pretty important parts of this polynomial already. Okay, so the last thing that we're asked to sort of consider here is this idea of end behavior. Now when we talk about end behavior, what we're looking at is we want to know what is our function doing as x approaches positive infinity and negative infinity. So in terms of understanding end behavior, it's what is the curve doing? Specifically our y values of our curve. So what is the value of the function of the value of the curve? What is the curve doing as x goes to negative infinity and x goes to positive infinity? This is a concept that we're going to see popping up at the beginning of calculus in terms of limits. So this is a nice thing to kind of wrap our brains around now. So we can do this a couple ways. I might suggest using that leading term or that dominant term to help us sort of predict what's going on. So if we've identified the lead term, so if we look at the leading or the dominant term, this is really the term that's in charge. So as x starts to get really big positive or really big negative, all the other terms really are not going to have much influence on the behavior of the curve, and that dominant or leading term is really going to take charge to determine whether it's going to go up to positive infinity or down to negative infinity on the y-axis. So if we looked at as x gets very big positive. So x is getting larger and larger and larger. And we were to look at our dominant term, or our leading term, which is 3x to the power of 5. Now, infinity is not a number, so we can't really plug it in, but we can think about what happens to this term as x gets infinitely large. So we could say, well, we'd have 3 times some infinitely large positive number raised to the power of 5. Now, if we take an infinitely large positive number and raise it to the power of 5, we are going to end up with a infinitely large positive number times 3, and 3 times an infinitely large number, a positive one, is just going to be an infinitely large positive number. So we can say that as x approaches positive infinity, then this is going to imply that our function g of x is also going to go to positive infinity, because that's where the dominant term is headed. We can also look at the other end of the end behavior, which is as x goes to negative infinity. So again, let's pull out that lead term, and we can say, well, what if in place of x we put a really big negative number? And if we took that really big negative number, raised it to the power of 5, since 5 is an odd power, that negative is going to be maintained. So we're going to have 3 times a very large negative number. And 3 times a very large negative number is just going to be a very large negative number. So what we can say is that our function g of x, as x goes to negative infinity, g of x is going to go to negative infinity as well. It's kind of a little abstract idea, but I think if you do enough of these, this kind of tends to make sense. So let's go ahead and do, let's try number 2. I think we're going to attack the same types of questions here. So the first thing is to find the degree. Now the tricky thing about this is that they've rearranged the order, so we don't want to just go for the first term. We want to find that largest power of x. In this case, the largest power of x happens to be 2. So we would say that in this case our degree is 2. And if we're looking for patterns about what the degrees will tell us, we might want to make note that this is an even degree polynomial. Okay, so next let's try the leading term. We're going to find that dominant term, and in this case the dominant term is going to be negative 3x squared, and we want to make sure that if there's a negative associated, we include that. So the leading term here is going to be minus 3x squared, and then our leading coefficient would just be this negative 3. So leading coefficient would be negative 3. Okay, and the constant term, if we go up looking for that, we would see that the constant term in this case is going to be the positive 4. Again, it's sort of misplaced in terms of where we might be looking for it, but that's going to be positive 4. So again, that would be our y-intercept. That's where it's going to hit the y-axis. Okay, so now we want to go ahead and sketch the end behavior for this polynomial. So again, we're going to go ahead and turn our attention to the dominant term. So our lead term was minus 3x squared. So let's see. As x gets infinitely large positive, minus 3x squared would be like taking negative 3 times an infinitely large number squared, and we could see that this is going to end up giving us negative infinity, because we'd square the positive infinity, which would give us an infinitely large positive number, times a negative coefficient would give us an infinitely large negative number. So in this case, we've got f of x here. So as x goes to positive infinity, f of x goes to negative infinity. And if we look at the other side of the end behavior, we've got that minus 3x squared, and in place of that x, we're going to see what happens if we put a really, really big negative number. Well, if we took a really big negative number and squared it, we'd get minus 3 times a really big positive, and then if we took that really big positive number, multiplied it by negative 3, this is going to hand off to negative infinity. So as x goes to negative infinity. F of x also goes to negative infinity. And the idea of sketching the end behavior, we could do something like this. If we could kind of just imagine our axes here. We could see, well, here's our x-axis, and then here's our y is equal to f of x axis. And over here we've got positive infinity, we've got negative infinity, here we've got positive infinity and negative infinity. So let's look at this first one. If we were to think about, well, as x goes to positive infinity, f of x or y values go to negative infinity. So as our x's, who knows what's going on in the middle here, but as our x's go off to positive infinity, then our y values are going to start dropping towards negative infinity. So our polynomial, at least the end of it's going to look something like that. And then also, if we were to consider, well, as x goes to negative infinity, so we start moving along the x-axis towards negative infinity, our function is going to head down towards negative infinity as well. So that's one way that we could sketch end behavior. And again, we don't know what's going on in between, but we can figure that out later. Okay, and now if we move on to number 3, we're going to find the degree of this polynomial. Now here we've got it in factored form. So one possible way to do this would be to multiply it all out, which might be a little bit obnoxious, especially if we don't have to multiply it all the way out. So one thing that we could consider doing here, if we just wanted to find the degree, is think about, well, if we did have to multiply it out, the largest power of x would be a product of each of these x terms. So if we did multiply it out, we know that the first term here would be x to the power of 4. And then we just have a bunch of other stuff kind of going on after that. So we can see that that would end up being the degree, that this would be a 4th degree polynomial. So if we were to consider the leading term, again, multiplying it out, we know that the leading term would end up being this x to the 4th. So we could go ahead and make that call. And the leading coefficient would just end up being positive 1. Now the constant term, again, the constant term is going to be the number that comes from multiplying all of the constants together. So if we had done that, if we multiplied -1 times -2 times -3 times -4, yeah, there'd be a lot of stuff in between, but at the end, that constant term would be the result of multiplying those 4 numbers together. And if you did, you'd end up with plus 24 by multiplying them all together. So this constant term is going to end up being positive 24. Now if you wanted to, you could multiply the whole thing out. It might be a little more clear, but this is just sort of maybe a quicker way to just get the first and last terms. Okay, so now we want to sketch the end behavior of the graph of this polynomial. So let's first identify the end behavior. So our lead term is just x to the 4th. So we could see that as x gets infinitely large positive, this function, and we're calling this function p of x, well, we're going to take that infinitely large positive number and basically just raise it to the power of 4, which is going to result in a infinitely large positive number. And if we let x get infinitely large negative, and then we take that value and raise it to the power of 4, since it's an even power, it will just make it positive. So we'd have positive infinity as well. And if we did want to kind of come up with a little sketch here, similar to what we did last time, and we thought, all right, well, there's our x-axis and there's our y-axis. So as x goes off to positive infinity, our function's going to take off to positive infinity. And as x goes to negative infinity, our function is going to take off to positive infinity. So we'd have something that kind of looks like this, and some other fun stuff going on in between. And we do know that there would be a y-intercept somewhere around at 24. Okay, so all 3 of those are kind of the same type of problems. Let's look at a slightly different one. So number 4, we're given a function g of x is x times x plus 2 raised to the power of 3. So we want to find the real zeros and their multiplicities. So zeros of polynomials are found, much like we find zeros of other functions, is we take the actual function. So if we want to find the real zeros first, we're going to take the function x times x plus 2 raised to the power of 3, and we're going to set it equal to 0 and then solve for x. Now, the nice thing here is that this is actually already factored for us. So since the product of these two factors, or I guess 4 factors, is equal to 0, then we know that either x would have to be 0 or x plus 2 would have to be equal to 0. And from this, we see that our two zeros would have to be x equals 0 or x equals -2. So these are the two zeros. Now, in terms of identifying multiplicity, multiplicity just sees, well, how often do those zeros repeat themselves in the course of our polynomial? Well, this factor right here, just the x factor, it only occurs once. It has one multiple, just x once. So the multiplicity of x equals 0 would be multiplicity of 1. Whereas since this x plus 2 factor, it happens 3 times. If we were to write this whole thing out, maybe we'd see that this is x times x plus 2 times x plus 2 times x plus 2. So that 0, or that factor, repeats 3 times. So because of that, this particular 0 has a multiplicity of 3, occurs 3 times. Now, something that we can pull from this idea of multiplicity is we get an idea of what the curve is going to look like, or going to do with those zeros. Both of these have an odd multiplicity, and as you probably talked about in class, zeros with an odd multiplicity usually can be seen on curves because the curve passes directly through the x-axis. It doesn't bounce off like it would with an even multiplicity. So that's why it's nice to be able to recognize these. Okay, so now we want to make a sign chart for this polynomial. These sign charts are a lot like they'll probably remind you of what we did with inequalities. And what we'll do is we'll just go ahead and we'll draw a real number line. And that's going to go from -infinity to +infinity. And this is going to give us an idea of when our polynomial is positive, meaning above the x-axis, or when our polynomial is negative, or below the x-axis. So those transitions are going to occur at the zeros. So I'm just going to go ahead, I'm going to plot the zeros that we have on this line. So here's where our polynomial has 0. And remember, zeros are just like x-intercepts. So these are x-intercepts here. Now, here we just go ahead and we pick test points. So, kind of like we did before, I'm going to pick -10 there. How about -1 and then +10? And if we tested these, so if we took our function, which we have called g, if we take g of -10, well, all we're interested in is whether or not this is going to be positive or negative. So here we would have -10 times -10 plus 2 cubed. Let's think about just the sign that's going to come out of this. We're going to have -10 plus 2, which will give us a negative number. We cube a negative number, we're going to get back a negative number. We're going to multiply that by a -10, and we're going to get a positive number. So what we could say here is that, well, this is just going to be some negative number, the -10, times some negative number. And we know that this is going to result in it being positive. Might seem a little confusing. Let's do it. Let's do it again just to kind of get the idea here. So if we picked g of -1, all right. So let's see what happens if we put -1 in for x, that first factor, because we're going off of this function up here right now. So that's going to be a negative number right there, and then we're going to have -1 plus 2, which is going to give us a positive number cubed, which would just give us a negative times a positive, which would result in a negative value there. And then lastly, we could pick positive 10. So if we plugged positive 10 in for x, that would just be some positive number. And then we'd have positive 10 plus 2, which would be some positive number, cubed. So we'd have a positive times a positive, which would result in a positive number. There's absolutely nothing wrong with actually plugging the numbers in and actually getting a value determined positive or negative, but if you're looking just to get quick and dirty whether we've got a positive or a negative on that interval, this might be something you might want to consider. So that gives us our sign chart for this polynomial. So we could imagine that on this interval right here, our polynomial is living above the x-axis because it's positive. Then on this interval between -2 and 0, it drops below the x-axis because it's negative. Then after 0, this polynomial becomes positive and goes back up above the x-axis. So we can kind of have a rough idea of what this curve is going to look like. So let's go ahead and put all of this sort of to practice with this last one. In number 5, we want to start by finding the y-intercept of this graph. Well, we know that if we ever are asked to find the y-intercept, all we need to do is take our function and evaluate it at 0. So if we do this, we'd have -2 times 0 plus 3 times 2 times 0 minus 1 quantity squared. This is going to give us -2 times positive 3. 2 times 0 is 0. Minus 1 would result, square the minus 1, we get a positive 1. And that we end up with is -6. So there's our y-intercept. Y equals -6. Now we want to determine the end behavior of this curve. And to do that, as we've done before, it's really helpful to have that dominant term. So I'm going to go up here and see if we can kind of work on getting a dominant term out of this. This might be a little obnoxious to multiply the whole thing out, but we can at least get started just to identify what the lead term would be. So we've got -2 times x plus 3. If we were to square out this 2x minus 1, we'd end up with 4x squared minus 4x plus 1. I'm going to go ahead and just distribute that 2 into the minus 2x minus 6 times 4x squared minus 4x plus 1. So the dominant term is going to arrive from us multiplying the two dominant terms of these two factors. So if we were to multiply this number or this term and this term, that would result in being the term with the highest power associated with x. So by multiplying those two together, what we'd see is that our lead term would end up being -8x cubed. So this is going to be our lead term. So we're going to use this to help us find to identify the end behavior. So we've got our lead term of -8x cubed. And now we just think about what happens here. Well, as x goes to positive infinity, we'd have -8 times a large positive number cubed, which would result in -8 times a very large positive number, which would result in a very large negative number. And if we used x approaching minus infinity, with our lead term, we'd have -8 times a very large negative number cubed. Cube a negative number, you're going to get back a negative number. So we have -8 times an even larger negative number. Multiply those two together, a negative times a negative is going to give us a positive huge number. So we can write our end behavior as x approaches positive infinity, our function, which is little p of x, is going to go to negative infinity. And as x approaches negative infinity, our function, little p of x, is going to go to positive infinity. Okay, so we're going to hold on to that because we're going to need that for the graph later. Next, we're asked to determine the zeros of our function and identify their multiplicities. So let's write up our function again just so we can, it's kind of off screen now, but it was p of x is equal to minus 2 times x plus 3 times 2x squared minus, excuse me, so that was minus 2x minus 1 quantity squared. Double check that. Okay, so there's our function. So we know that we can determine the zeros by setting the factors equal to 0. So let's go ahead and do that. So we've got, if we take minus 2, x plus 3, 2x minus 1 squared, set that equal to 0. We want to figure out which x values will zero this out. So the negative 2, we could just divide both sides by negative 2 and get rid of that. So that's of little importance for the zeros. So now we can set each of these factors equal to 0. 2x minus 1 squared equals 0. Solve for x here, we're going to get x equals negative 3. Solve for x here, take the square root of both sides, add the 1, divide by 2, we're going to get x is equal to 1/2. Okay, so those are our two zeros. So I'm going to go ahead and write these up here. So our two zeros are x equals negative 3 and x equals positive 1/2. Now we need to identify the multiplicity of these zeros. So how often do these occur? Well, if we go back up here, we see that the x plus 3 was just a factor once. So this has got a multiplicity, I'm just going to abbreviate that, multiplicity of 1. Whereas the 1/2 was associated with this factor right here, the 2x minus 1 squared. So that factor occurs twice. So we say that this has a multiplicity of 2. Now, what is this going to imply for our graph? Since this is an odd multiplicity, we're told that this results in our curve passing through the x-axis. So it passes through the x-axis at that 0. Whereas since it's an even multiplicity with 1/2, so this is an even multiplicity, this means it's going to rebound off the x-axis at that particular 0. It just kind of goes right to it, hits it, and then bounces right off and goes back to where it came. All right, so let's see how all of this fits together to get a graph of p of x. So if we set up our axes here, this is not going to be perfect, but it's enough for us to kind of get an idea of what the curve looks like. You've also got your graphing calculators, which would make this painfully easy and horribly unfun. So let's lay down what we've got. We've got our y-intercept at negative 6. So 1, 2, 3, 4, 5, 6. So here's negative 6. We've got a 0 at negative 3, negative 1, negative 2, negative 3. And then we've got a 0 at 1/2, which would be like right here. So that's 1/2. All right, so we start plotting these points. Here's our y-intercept. Here's an x-intercept. Here's another x-intercept. So end behavior tells us that if we're starting over here on the negative side of the x-axis, that as x approached negative infinity, p of x is going up to positive infinity. So our curve is actually going to be coming down from positive infinity here. So it comes down, it approaches this 0, and since it's got since this 0 has an odd multiplicity, it passes through the x-axis. So it's just going to go through, and then we're not exactly sure what it's going to do next. Maybe it passes down, but as it approaches the y-axis, it's going to have to hit that y-intercept. So maybe it comes down and it comes back and hits it right there. Now it's going to come back up towards this one, and it actually is going to rebound because this 0 has an even multiplicity. So maybe it came up very steeply and then just sort of bounces off. And then the end behavior as x goes to positive infinity, we know that p of x is going to go to negative infinity. So it looks like this. not a pretty drawing, but you get the idea of kind of how this is shaping up as a curve. And if you graphed this, you'd probably get something that looked a lot nicer, but same characteristics. Okay, so that should do it for this one, and I'll see you all in the next video.